So projectile motion. Yeah, this is going to be one of those things that you're going to see all throughout the year. It's going to be included in a bunch of different ways, and you'll understand what I mean later on. But trust me when I say that this is going to be probably one of the most important units that you need to know conceptually and mathematically. So projectile motion, we were working with one direction the entire time, and what projectile motion does is now it combines both directions, the x and the y direction. So projectile motion uses the previous concept to handle two-dimensional free fall problems. As this free fall, and in free fall, the acceleration in the y direction is equal to g. There is no acceleration in the x direction for a projectile. So as you can see here in this picture I stole online, this horizontal velocity is not changing throughout the entire thing. If this was 1, it'd be 1 all the way around. This means that there's no change in velocity over this time interval if each one of these dots were a second. So that means there's no acceleration. Meanwhile, you look at here at the y direction of all these velocities, you see that it's decreasing and becomes 0 at maximum height, and then it gradually increases on the way down. Means that there is an acceleration, and this acceleration is g pointing downwards towards the ground. So as you can see here, it's going to take away and it's going to go all the way to where it's going to point the object's velocity in the y direction straight down. The x component of the velocity is not changing, which you said again, there's no acceleration. The y component is constantly changing in the downward direction. So it's constantly changing, meaning that it's going to be at there's going to be an acceleration that doesn't change at all, which is that g again. These two components can always be put back together to get a total speed. So if you look here, this is basically a demonstration of this right here. So if we were to get any point, and I'm using, let's say here, you'd call this Vx, and you'd call this Vy. If you add these two vectors up, you'd get this value right here. This is going to be this added vector of Vx plus Vy. And this is going to be V. But the thing is, this isn't just like, you don't just add these vectors since these are values. So you're going to do Pythagorean theorem to figure out what the actual value of this thing is. So you get V squared is equal to Vy squared plus Vx squared. And you square root this thing till you get this value right here. So if you have the x component and the y component, you can figure out what this would be in the end. So what this would be, what that would be. This one would just be this only x component because this would be 0. And then you can figure out what that is, what that is, what that is, and all the way. Projectile motion. A red and yellow ball are released at the same time. The red ball is released from rest, while the yellow ball has an initial velocity directed to the right. So I can't draw this one here because black on black is not right. But the yellow ball has this V pointing to the right. And it's directly to the right. It's not at an angle or anything. Though the yellow ball is never traveling at the same speed and definitely covers a greater distance, by the time it strikes the ground, it will not take longer to strike the ground. Okay, I stole this PowerPoint, I'm going to be honest. And this makes absolutely no sense. But basically what they're trying to say is that even though this yellow ball is moving to the right and it's getting away from its initial spot, it's going to land at the same time on the ground as this red ball that just drops straight down. They both start at the same height, and there's no additional velocity in this yellow ball that's helping it go down faster. So if you can basically think of this yellow ball as the red ball whenever it comes to the y direction. It's just going to fall straight down, and it's going to take the exact same time as it, just like this red ball whenever it's dropped straight down. So don't get thrown off with the fact that it's pushed to the right. It's going to have a velocity to the right, and that means that it's going to take more time or less time. That's not the case. It's going to be the exact same as if you were just to drop it straight down. Projectile motion. The horizontal and vertical components of an object undergoing projectile motion are independent of each other. Though the directions are independent, they are still linked by time. Time is the same for both directions. So what this means is basically the speed of in the x direction cannot be the same as, you cannot use this speed in the x direction to calculate the speed in the y direction. They change at different rates. For the y direction changes at that negative g acceleration, while the x direction, it doesn't change at all. So you can't say, oh, since if this doubles, then this must double. No, that's not how it works. The only thing that you can say that both of these are the same as is their time values. So if time equals 1 second, 1 second has passed here, 1 second has passed here, and you can figure out where the projectile is at that time. Alright, so this is where you get to the actual algebra / physics stuff. So in the y direction, you use these three equations. The y direction is this blue ball right here. You see that this blue ball is dropped straight down, and it's the same as, and if you can see, it's the same time as the actual projectile, as the red ball right here. So you see that this red ball is, after 1 second, it's going to be at this height. After 2, after 3, after 4, after 5, after 6. It's going to be the same thing as if it was dropped straight down. So what you can do is you can picture this as the red ball, but you can picture the red ball as if it was the blue ball when it comes to just being dropped straight down. So in the y direction, you can use these equations. The velocity final in the y direction is equal to the velocity initial in the y direction plus acceleration in the y direction times t, which this, if we call upwards positive, this is going to be negative gt. And then the same thing here. These are just all the kinematics except replaced with the vx or y is going to be replaced with, every x will be replaced with y, because this is the y direction. Now, in the x direction, you only have this equation written. And this is because in the x direction, this is a constant horizontal velocity. A constant velocity means that acceleration is equal to 0. So if you try to use any of these values, you get a 0 plugged in here, you get a 0 plugged in there, you get a 0 plugged in there. So for this first and third one, you just get vx is equal to vx. Vx squared is equal to vx squared, which is like, yeah, it's useless to me. You won't use it at all. Meanwhile, on this one, you get this term is equal to 0, so you get x equals x initial plus v initial in the x direction times t plus 1/2 axt squared. We just said that a is 0, so this zeroes out, and you get x equals x initial plus v initial in the x direction t, and then if you subtract this x initial, you get x that, and then you get that theta x, or the displacement, equals v initial x times t, which is this equation again. So again, note that the velocity is constant since the acceleration is 0 in the x direction. The x component of the velocity does not care about the gravitational acceleration. Keep in mind that if you were to draw, or not draw, but if you were to take, in fact, if you wanted to figure out what is causing this ball to head downwards, it's only that g value. It doesn't have anything else affecting it. Maybe you can say that, okay, the air resistance would go for it, but air resistance is so small that we don't care about it. You can think of the air resistance as like ants. You see it there, but you just step on them anyways. You don't really care about it at all. Alright, so this is like this is the first problem of many torture problems that I'm gonna show with you guys, because this is like actually really important. So I just copy and pasted this picture from here, except I gave it value this time. So what I'm looking for is for this value right here, which I'm going to call which is called question mark, but I'm going to call it D. Or I'll call it R. R looks cooler. Alright, so you have 5 meters per second in the y direction. It's going to fall this much time, and we're looking for this R. So we know that for the x direction, we can only use delta x equals vxt. Well, we know that delta x is what we're looking for here. It's the same thing as r. So we can just replace r vxt. Now remember that we said that the time is the only thing that connects the both x direction and the y direction. So if we look at the y direction, oh, by the way, we know what Vx is. Vx is equal to 5 meters per second. But we're leaving it in variable form for right now. So in the y direction, if we use, I believe it's the second kinematic. If we use this equation, you get that v initial t plus 1/2 a y t squared. That's one equation with that. Or we get v final in the y direction is equal to v initial plus at. Now, the plan is we got to solve for t in one of these two. So we can plug it into here, and since we have this value and we know all the values that are here, then we shebang, we figure out what this r is. Now, the thing is, if you wanted to get the t value from this junk, it's going to take quite some time. So if you're a normal person, you'd use this as your, because you're just trying to solve for t, you just do a couple steps. Now, if we look at the ball vertically, it has no vertical direction or vertical velocity it has no velocity in the y direction. It's just you can think of it as, again, being just dropped straight down. So there's nothing in the y direction. So this zeroes out. And then you think, okay, how do we figure this out? Well, there's a problem now. You don't know nothing about Vy, because you don't have how much time it takes for it to fall. You only have this distance. So even though you think it would have been easier to use this question because you just have to divide by a and you get this, you don't know what Vy is. So I tricked you guys. Sorry, not sorry. And now we have to use this. But wait. What did we just say? This v initial in the y direction is 0. There's no velocity in the y direction. So this zeroes out. We get this though. Okay. If we multiply 2, divide by a in the y direction, we get 2 delta y over a in the y direction equals t squared. We square root both sides, and we get t is equal to the square root 2 delta y over a y. Oops. A y. Alright. AY is equal to either positive 9.8 or negative 9.8. It depends which way we're looking at it. Let's call, in this case, down positive. In one case where down is positive, that means that since the 9.8 is always pointing towards the ground, it's going to be a positive 9.8. And this also means that from 0 to 25, it's going to be positive 25 meters. So we get that the square root of 2 times 25 meters over 9.8 is equal to t, which equals 2.26 seconds. Alright, we found the time. It took us a while, and I tricked you in the process, but we found the time. It wasn't that bad. So now, we can plug in this time of 2.26 seconds into this original equation, or into this x direction, because again, remember, we're looking for this r. R equals Vx, and we said Vx is 5 meters per second, times 2.26 seconds. And if you look here, the seconds cancels out, so you're left with meters, which is the distance traveled here. So it makes sense why that's that. And we get R is equal to 11.3 meters. And that's the answer for how far this thing travels. So you see that even though we were looking for this value, we still included the y direction because we needed the time. We can't figure out the time it takes from go to here if we don't know how far it's traveled. But we can figure out the time it takes from here to here since we do know how far it's traveled. So you can plug in this t value from y into this x, and you can figure out how far it went. The same thing if it was vice versa. If you didn't know what this length was, but you knew what this was, you can solve for t over here in the x direction and plug it back into the y. So you can see that time is the thing that you're going to solve for in one of these parts, in the x or the y direction. And then you plug it into the other direction, and then you figure out whatever you need to find out. Alright, so here's a more complicated problem. We have a football kicker. We have a football kicker and a football. A football is kicked 1 meter from the ground. So 1 meter from the ground, which this says, so from here to here is 1 meter. 1 meter from the ground at an angle of 30 degrees with a velocity of 15 meters per second. So if we were to zoom in to this position right here, we'd see this. 15 meters per second at an angle of 30 degrees. Well, you might be wondering, where exactly is this angle at? Well, whenever you're given an angle on a projectile motion problem, you can assume that the angle is with respect to the horizontal. And what that means is any horizontal. So, but in pointing in the same direction as the velocity. So if I was to draw a horizontal line right here, the angle would be right here. Now, let's say that the velocity is pointing this way. Well, with respect to the horizontal would be that this would be the angle. And then if I do go like this downward with respect to the horizontal would be the angle. So you can see that in projectile motion, whenever you're given an angle, you can most likely assume that the angle is with respect to the horizontal and point in the direction of the velocity. So then we have, it says here the angle is 30 degrees, and we said the velocity is 15 meters per second. Calculate the max height above the ground, total time in the air, total distance traveled, velocity vector at max height, velocity when the ball hits the ground. Okay, that's a lot of parts, but this is important stuff, so it's good that you guys are reviewing this right now. Alright, this is part A. Max height above the ground. Alright, so we know what the ground is. It's the grass. So what we can do is, if we pretend that the ground was right here, it makes everything a lot easier. If you ignore this bottom part right here, you can picture it as just like a normal projectile. So you need to find the max height above the ground. Alright, so what direction are we looking at? Well, if we look at the x direction, it wouldn't tell us how far above the ground it is. So we're looking at the y direction. We're looking for this, whenever it's at the peak of its trajectory, we're looking for this value in the y direction. We can call this delta y. So, what do? Alright, we know that this is 15 meters per second and it's kicked in this at 30 degrees with respect to the horizontal. So, what we can use is we can use one of these equations. Delta y, v initial t plus 1/2 ay t squared, or vy equals v initial plus at. Alright, which one of these would give us the maximum height above the ground? Well, it's kind of a trick question, because you gotta remember, there's a third part. There's a third equation that you can use. Delta y. Okay, vy squared equals v initial squared plus 2a delta y. Alright, so we're not given any time here. Whenever you're not given any time at all, and you're looking for a specific direction, you can really just get rid of this and get rid of that. You're left with this question, and you're stuck with this, or not question, you're stuck with this equation, and you're only left with this equation. Alright, so let's think. At the maximum height, if we look back over here, we saw that the maximum height, it's only pointing in the x direction. There's only velocity in the x direction. There's nothing in the y direction. So the final y velocity at the top is going to be equal to 0. Because at the top, we have this. Here's the peak. We have this right here at the top. This is at top. At the top, there's only this v in the x direction. There's nothing on this y direction. So we say that this is 0. Alright, well, we have v initial y squared plus 2a delta y, and it's equal to 0. And what are we looking for? We're looking for this delta y, okay? Subtract this, y squared, divide equals 2a delta y, divide by 2a, negative v y squared over 2a equals delta y. Alright, well, we know what this a is. A is going to be g, and let's call positive upwards. So this a is negative 2, or this a is negative 9.8. How do we figure out what v initial in the y direction is? So we can square it, divide it by 2a, and we can get this y direction. Well, remember, we are given this initial velocity right here, 15 meters per second, and we're given this angle. Oh, that was bad data. I'll do that again for you. Alright, we're given this table, theta. V in the x direction is going to be right here. V in the y direction is going to be right here. If we remember, both of these squared, added, and square rooted will give you this final velocity here. But to save time, we know that this angle here is going to be 30. So if we take the sine of this angle, the sine of this angle is going to be equal to the opposite over hypotenuse. V in the y direction over 15. 15 sine theta equals Vy. 15, or we know that sine is equal to 30. So 15 sine of 30 degrees is equal to Vy, which is 7.5. Alright, we figured out what this was, 7.5. So this is V initial in the y direction. Alright, so now we can plug everything in. And again, it's pointing up, and we call it upwards positive. So it's pointing up. So this is equal to negative 7.5 meters per second squared over 2 negative 9.8 meters per second squared. And we get 7.5 squared over 2 times 9.8. We get that this delta y is equal to 2.87 meters. Now, hold on a second. The maximum height above the ground. This kicker kicked the football above the ground 1 meter. So what we needed to do really was delta y plus 1. So this isn't the final answer. Final answer is 3.87 meters. Because the football was already in the air, or above the ground 1 meter. What we did was we ignored the ground and we pretended as if it was if this x-axis was the ground. Now we can't pretend anymore, and we gotta add this missing distance right here, which was 1 meter. Alright, total time in the air. That's the next part. Okay, so we have this football kicker, you kicked it here, this right here is 1 meter, you hit it bang, 15 meters per second, this here, this angle theta is equal to 30 degrees, alright, and we're going to find the maximum time in the air. Alright, So you see, we're solving for time. So this is part B. Solving for time. This means we're gonna have to look in both directions. Alright. This is where these types of questions, whenever you're solving for time in the air, you can take multiple approaches to it. And as long as you get the answer in the end, you're right. But you also have to show the work with it. So that's the part where people can get mixed up. So what I would do is, okay, we know that the time in the air is going to be equal to time it takes to come up here plus the time it takes to come down here. So I can split this into two different parts. We know that the delta y for this right here is equal to 2.86. So right here, this is the first part of the trajectory. So this is the maximum height, and this is the parabola shaped thing. So with this first part, we know that this right here is 2.86 or 87 meters. Alright, we know in the x direction, there's this equation, delta x equals vxt, and the y direction, you have all these other equations. You have, I'll write this down here. In the y direction, you have delta y equals v initial t plus 1/2 ay t squared. Vy equals v initial y plus at. And then vy squared equals v initial y squared plus 2a delta y. Alright, since we're looking for time, you can't use this one. It wouldn't really help us in this case. Alright, we're looking for time. So, what you can do is you can remember that at the top of this, at the maximum height right here, there's only the velocity in the x direction. There's vx. So, from here to here, it's given, if you picture it as if it was, if you remember from back here, you can picture it as if it was as if this yellow ball was like this red ball. So if we go back to this, we can picture it as if it was being launched straight up, 2.87 meters, starting from a certain speed and ending at 0. And we can figure out easily the time it takes to go straight up like that. So in reality, we don't need an x direction time or the x direction at all in this case. Because if we picture that this ball was just going to be launched up, it's going to be thrown up with the initial Vy, it's going to fly up 2.87 meters and stop right here. We can figure out how long it takes using just regular old kinematics. Which one of these would we use? That'd be the easiest. Well, you can pick. You have delta y. If you can remember, this Vy is going to be equal to 7.5. You know what A is. You're solving for T. So you could use this one. You have all of these, and you could use this one. But since I'm a normal person, I would use this one right here. There's only one T. It's really easy to solve. So we know that at the final velocity is going to be 0. There's no velocity at the top of the P. We get 0 right here. 0 is equal, we got right here, v initial y is equal to 7.5 meters per second. 7.5 meters per second. A, if we're calling upwards positive is going to be negative 9.8 meters per second squared times t. Subtract 7.5 meters per second, divide by negative 9.8 meters per second squared equals t. You get 7.5 over 9.8. T is equal to 0.76 seconds. Alright, but remember, we split this up into two different problems. So now, we got to look for the rest of this. So now we're looking at the second part. Now, we said this is the height at the top. Remember, only Vx. Well, we know that it's asking for the total time in the air. If we were to use this same height, it would stop right here. It's still in the air. So we need to take into effect the total time, the total height above the ground. It's going to be now this 2.87 added by with 1 extra meter. So now it is 3.87 meters. So now you can think of it as another projectile. If you were to picture this just in one single spot, where this height is 3.87, and now it's starting from up here and going, it has no initial velocity in the y direction, and now it's going to end up down here with of vy. Then you can easily again figure out the time it takes to fall all the way down. Now, however, in this case, you don't know what this Vy final is unless you have the time. So you're stuck with this first equation up here. You're going to get this delta y equals V initial t plus 1/2 ay t squared. But the V initial in the y direction is 0. So this zeroes out. Now we have this same situation as we had earlier, which leads us to 2 delta y over ay square rooted equals t. We know what this delta y is. If we're calling upwards positive still, just like how we set up here, then it's going to travel negative 3.87 meters. So this is 2 negative 3.87 meters over, and since gravity, g is always pointing towards the ground, g is also negative, so negative 9.8. So we plug this into our calculator. You get that 2 times negative 3.87 over negative 9.8 is equal to 0.89 seconds. Now, although you can check yourself by plugging in all the numbers and checking everything, it makes sense, the numbers that we came up here, for the time to go up and the time to go down. On the way up, it had to travel less meters, with the same acceleration, of course. It had to travel less time, or less distance. And we know that distance over time is, or not distance over time, but we know that time is affected by how long it's going to travel, or how long it's going to be traveling, how far it's going to be traveling, sorry. So it makes sense that this time going up is shorter than the time going down, because it traveled a longer time period. So we get the time in the air is equal to 0.76 seconds plus 0.89 seconds, which is equal to 1.65 seconds in the air. Alright. Total distance, part C. Total distance. So again, we have this ball launched that way with a V and a theta. V is equal to 15 meters per second. Theta is equal to 30 degrees. Okay, we're looking for the total distance it's traveled. So it's going to hit the ground right about here. So we're going to be looking for this value right here. the d value right here, total distance. Okay, so what direction are we going to be looking at? We're looking at the x direction. And the x direction only has this delta x equals vxt. Well, if we look back at the equation from last time, we figured out the time it was in the air. And this is the same thing as the time in the air. It's the same thing. It's the same ball, the same football being kicked 1 meter above the ground at 15 meters per second at an angle of 30 degrees. It's the same thing. So we can use that time from the previous equation, or previous section, and plug it right back in. So now we save so much time, and now we know 1.65 is the time it takes. 1.65 seconds is the time it's going to be traveling in the air. Now the thing that we don't know is this Vx. But if you remember, 15 meters per second is made up by these two portions right here, and this theta is equal to 30 degrees. We figured out that Vy is equal to 7.5. If this is Vy, that means this is Vx. So now if we do the cosine of this theta angle, we get the adjacent, which is Vx over 15. 15 cosine theta is equal to Vx. So now 15 cosine of 30 is going to be equal to Vx, which is equal to 12.99. And I'm going to leave it like that because I know some of y'all would want to round up to 13, but no, I'm going to trigger all of you guys. So delta x, we just figured out what Vx was, 12.99 meters per second, 1.65 seconds from the last part, 12.99 times 1.65. Delta x is equal to 21.4335 meters. Yeah. Alright. Part D. It's asking for the velocity vector at the maximum height. Okay. Velocity vector at the maximum height. So here's our projectile, right? At the maximum height, I've said this about 5 times already, so if you don't know what I'm about to say, I don't know what to tell you. I just pay attention, I guess. At the max height, it's only going to be the Vx that it started off in. So this Vx, there's no acceleration in the horizontal direction. So this Vx is the same all around. So if we get the Vx that was right here, we can figure out what the Vx that was up there. Now, in this last part, we just did this, but I'm going to do it again because I know some of y'all might have blinked and missed the whole part. So I'm just going to do it for you guys really quickly. Vy is this way, Vx is this way. We got this angle right here. Cosine of this angle is equal to Vx over 15. Do math. Vx is equal to 12.99. Alright. So the velocity vector is going to be this. Velocity is equal to the square root of Vx squared plus Vy squared. Because if you look, this would be Pythagorean theorem, this squared plus that squared equals that squared. But since we're not looking for this squared, we just square root everything and we get this. Since we know that there's no y velocity at the maximum height, this zeroes out. So we get v is equal to the square root of Vx squared. Well, we know that the square root and the squared cancels out, so v at max height is equal to Vx. So v max height is equal to 12.99 meters per second. Alright, final part. Part E. Velocity when the ball hits the ground, or the velocity vector when the ball hits the ground. Alright, this is different. We have this projectile path. Alright, we know that this Vx is going to be like this, and it's going to stay constant all throughout. Okay, that's not constant. This is going to be the same. So we know that our answer is going to have this Vx at the end. But what about Vy? Well, Vy had a part right here, and we calculated earlier, it was 7.5. But Vy started off strong, and it got gradually worse until there was nothing here, and then it started pointing downwards. So this V vector is going to be these two. It's going to be equal to Vx squared plus Vy squared and then square rooted. Alright, so now the problem is we got to figure out what this Vy is on the way down. We calculated earlier from part B that on the way down it took 0.89 seconds. So we got to remember that. So 0.89 seconds to go from here to here. In the y direction, remember we have these equations. We have delta y, v initial t plus 1/2 at squared, or we have v equals v initial plus a t squared. Oh, oops, not squared, not squared. At. Alright. So we're going from here to here. We're looking for this again. I believe it was 3.87 meters. 3.87 meters. Now we know that time it takes 0.89. Starting from up here with nothing, it's going to end with down here with something. So we're looking for after 3.87 meters or 0.89 seconds fallen, what is this velocity in the y direction? Well, we can easily figure this out. I'm not going to use that. I'm using this. V initial, 0. This is what we're looking for. This is Vy final. We know that A, if we're calling downwards positive, we know that A is 9.8 meters per second squared. T, calculated earlier, 0.89 seconds. 9.8 times 0.89. Vy is equal to 8.72 meters per second. Now, what we're looking for is the velocity vector when the ball hits the ground. So we're not looking for Vy or Vx. We're looking for V, which is these two. So if we remember, V is equal to square root Vx squared plus Vy squared. Remember that earlier we figured out that Vx is equal to 7.5. So V is equal to the square root 7.5 meters per second squared plus 8.72 meters per second. And that squared. Finally, to end this second torture problem, I think it was the second one, I don't know. We get that the V velocity vector whenever the ball hits the ground is equal to 11.5 meters per second right here. Alright. Next torture question. Yay! Alright. We have this guy here that's about to kick a soccer ball this time. At an angle 35 above the horizontal. It's going to travel 30 meters. And there's going to be a wall, distance d, which is 1.8 meters. What is V initial? What is the velocity initial? How long does it take to get to the wall? Alright. Okay. So this is going to be a complicated problem. We're looking for V initial. V initial is right here. We have this data, and we know that this is Vx and this is Vy. We don't know what this is. This is what we're looking for. So what can we do? Well, we know that this ball is going to clear this height right here of 1.8 meters. The ball is going to end up here. It's going to, after 30 meters traveled, it's going to end right here. Okay. Sorry. These questions suck sometimes. I forgot what the plan was. Yeah, okay, sorry. So, plan is x direction, y direction. The x direction, we know that this is going to be delta x equals vxt. Alright. No, we know that delta x is this 30 meters. So, I'm going to call it r. So, r is equal to vxt. Okay, in y direction, we have this delta y is equal to v initial t plus 1/2 ayt squared. Alright, this delta y is d, which is 1.8. This v initial in the y direction, t plus 1/2, and we know that this a is going to be g, and we're calling upwards positive, so this is negative g t squared. Alright, one thing that you're going to need to get used to is that you can change what this vx is and what this vy is. Oh, you know, why am I writing this triangle? Okay. This is the angle right here, and we go angle is 35. We can rewrite that the cosine of this angle is equal to vx, v initial. So v initial is equal to cosine x. V initial cosine of theta is equal to vx. We can plug that into here. So r is equal to v initial cosine theta t. The plan is now, if we solve for t here and plug it into here, we can solve for this v initial. This, again, is v initial in the y direction. This is vy, same thing. So we can rewrite the sine of this theta is equal to vy over v initial. V initial sine theta is equal to vy. So we can replace this with d equals v initial sine theta times t minus 1/2 g t squared. If we solve for t here, we get r over v initial cosine theta equals t. So now we got to plug in this t value that we found into here, because we're not getting a t. d equals v initial sine theta times r v initial cosine theta minus 1/2 g r over v initial cosine theta squared. Alright, so what we can figure out right here is this v zeros cancel. This one doesn't. So we rewrite d is equal to r sine theta over cosine theta minus 1/2 g r squared over v initial cosine theta squared. We're solving for this v initial, so we can add this to this side, subtract the d. We get 1/2 g r squared over v initial cosine theta squared equals r sine theta over cosine theta minus d. You multiply the v squared v initial cosine theta squared to the other side, and then you get, I'm not writing all that again, so understand that I'm going to multiply this to the other side, and you get this times v initial cosine theta squared. And then since these two are being multiplied together, you can divide by this entire mess. So then when you divide by that, you divide by this mess. Oh my god, this is painful. You get, oh, what did I just erase? Okay, r sine theta over cosine theta minus d is equal to this is equal to v initial cosine theta squared. You square root both sides, so you finally get this. And then you realize this cosine of theta is being multiplied to this, so you divide by this cosine theta, and you can get v initial equals the square root of 1/2 g r squared over r sine theta over cosine theta minus d. Okay, wait, I'm going to redraw that. Radical sine. What just happened? Okay. Square root of all this junk divided by cosine theta equals this v initial. I plugged this into my calculator earlier, so I am just gonna tell you guys it's equal to this v initial, what he has to kick the soccer ball at this angle of 35 degrees. Is equal to 18.50 meters per second. If you want to plug this in, G is 9.8, R is 30, D is 1.8, and this theta is 35 degrees. So that's if you want to plug that in. And what we did with this question is we solved for something that we would need time for without using that time value. So you see here, we had time in both of these equations that we had. But since we can easily solve this and rearrange it for time, we can plug in this value into this time value right here. And this makes things, this is why projectile motion is one of these complicated and really hard things to get a hold of. Because sometimes you need to figure out how to solve an equation that uses time without being given time, and there's no other way around it. So you're going to plug in, you're going to solve, usually at least, you're going to solve for this in this x direction, time, and then you plug that into the y, and then you do a bunch of algebra like we did here, and then you can figure out what this answer is for the v initial. Alright, next torture question. What is the range of values v initial that you need to land in between m and n? This is a fun question right here. I'm gonna let you guys know this. Alright. Well, fun to me at least, because it's weird. It's a weird question. You probably hate this question. And I'm gonna call this question. I'm gonna call this question. I need a name. I'm gonna call this question I'm gonna call it question. Yeah. That sounds about right. Okay. What is the range of values v initial that you need to land in between m and n? Alright. What we know is this. the distance from this point O to M is 30 meters. The distance from O to M to O to N is 40 meters. So this ball has to land in between 30 and 40 meters. Alright. I'm going to let you guys think about this real quick. Okay. Think you've had enough thinking? And by thinking, I mean you've probably given up by now. Alright. So I'm going to teach you guys something that y'all can use forever now. D, which is the distance from here to this certain point, then we'll call this D, is equal to V, Y, T plus 1/2 AY T squared. Keep in mind, this is rewritten from the delta Y equals blah, 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 blah. Okay. We know that Vy can be rewritten as V0 sine of 30 times T plus 1/2 AY T squared equals D. Okay. There's 2 times whenever this ball is at 0. Oh, this is my bad, okay. I'm sorry. This is D. This is D, not that one. This is D. Alright, I'm gonna restart. So I'm calling D, this value height, is height right here. So D is equal to Vy, blah, blah, blah. D is equal to V, we wrote Vy right here. Okay. There are 2 times whenever this D value is equal to 0. At the beginning and at some time. If you think of this, you get this. You're looking for whenever it's 0 the second time. So 0, if we say that D is going to be equal to 0, D, or 0 equals V initial sine of theta times T plus 1/2, and I'm just going to call up as positive again, negative 9.8 T squared. Okay. If we factor out a T, we get V0 sine theta minus 1/2 9.8 T equals 0. So we can, by looking at this like that, we factor out a T, we get that this T, we can figure out what exactly these T's are for whenever the distance traveled is 0. We know that for this T, if we set it equal to 0, T is equal to 0, which is the beginning part on the graph right here. If we set this junk to equal to 0, we can figure out the second time it's 0 meters above the ground. So it's on the ground. 0 equals V initial sine theta minus 1/2 9.8 T. I'll bring this up here. We get V initial sine, I'm going to write 30 equals 1/2 9.8 times T. If you divide by that, you get V initial sine 30 over 1/2 9.8 equals T. So this is the time it takes for that ball to hit the ground. And this is like a shortcut. So if you want, you could say this: v initial sine of theta over g, and this 1/2 becomes a 2 because, yeah, equals t. So if you're looking for the time it takes to travel, the time for a certain distance, so if you're looking for the time it takes from go to here to here, and you know the initial speed, and you know the angle it's at, and you know what g is, which I really hope you guys know what it is by now, you can figure out the time value at which it stops. You can't figure out the distance that it travels, or you can't figure out the height it is. You can figure out the time where it hits the ground. So this is one of those shortcut equations that are never given to you, but it's true for all values of v initial and theta with that g, and it will give you that correct t. In this case, we have this. So what we're solving for is the range of values of v initial that you need to land in between m and n. Okay. We need to find that range of values that is given to that m, between m and n. Well, we figured out what t was. We need to figure out where the range is here. So now we're back in the x direction. Delta x is equal to vxt. Vx can be written as v cosine theta. We just solved for what t was. T is equal to v2 v initial sine theta over g. So delta x, whenever you multiply this, you get 2v initial squared cosine theta sine theta divided by g. So this is this delta x. This is the distance at this time that you can figure out. Now this is another shortcut question. It can be written as this as well. Sine of 2 theta over g. You'll learn that 2 cosine of theta times sine of theta is equal to sine 2 theta. You'll learn that later on in pre-cal. But this is another shortcut question. Now this is given, this is the horizontal distance at a certain v with this sign divided by g. So this is another shortcut that you can find, this horizontal distance. Now what we need is this to be between 30 and 40. So what we can do is we can set this up, not equal. And now, oops, we forgot the square. And now we can figure out what values of v0 have to go in here. What I would do if I see something like this is I would break it up so you get this. And you get this. If you solve for each, you get, you know what theta is? I forgot what it was. 30 degrees. Theta is 30 degrees. And you're solving for this v initial. So you get 30g over sine of 2 theta square root is equal to, or has to be less than v initial. And you get over here, v initial, 40g over sine 2 theta square root. So g, again, if you don't remember what g is by now, you're in my prayers. 2 times 30, 16. Okay, yeah. We get this value is 18.43 meters per second. Is less, has to be, I forgot how to read these things. V initial has to be greater than 18.43 meters per second, but less than 21.28 meters per second. So this is the range of V values that you could have to land in between M and N, or 30 and 40 meters. Now, these two equations, I wouldn't memorize them because you could solve for them and figure it out. But if you do happen to memorize them, now I'm not saying you should because it's a cheap shortcut, but it's a very useful cheap shortcut. It will save you a bunch of time. So use these at your own risk, because if you memorize these and tend to only use these, you tend to forget completely the whole concept of projectile motion. So if you got the hang of all this stuff without using, if you could solve these couple of questions up, the questions we did before, then okay, yeah, you could probably memorize these and you'll be fine. But if you're still struggling with the questions we did in the past, I wouldn't recommend memorizing these, because then you'd get so used to only using these, and let's say one day you forget it, you don't know what to do at all, and you're screwed for your test or the exam or whatever. Alright, final one. Oh god. What is theta? We're looking for the theta now. Okay. Okay. Let's process this. What is theta? Okay. We know at the peak there is no Vy. It's only Vx. And we have this distance right here. If we look at the y direction, not delta y, if we look at the y direction, you have these equations. T plus 1/2 ay t squared. Vy equals V initial plus AT, and then Vy squared equals V initial squared plus 2A delta Y. Okay. So what we need to figure out this theta is we have this and we have this. We're looking for this theta. What we need is one of these. We need this Vx or we need this Vy. You need one, and then you can use trig to figure out what that angle is. So I pointed out that we should look in the y direction. What this would look like is 4 meters up here, and it's going to be thrown up, and it's going to stop. It's going to stop right here. You have 4 meters, and you're looking for this Vy. You know that this V initial y, and this is Vy. So Vy is equal to 0. V initial y is what we're looking for. If we're calling upwards positive, then, and we rearrange to solve for this V initial y, we get this. Negative 2A delta y is equal to V initial y squared. You square root negative 2, negative 9.8, 4. It's negative 9.8 because I called upwards positive. Square root 2 times 9.8 times 4. We get V initial y is equal to 8.85 meters per second. So we figured out what this was. I can now if it will let me, gladly erase this and replace it with 8.885 meters per second. We have two sides and we're looking for this angle. We know that the sine of this angle is going to be equal to 8.85 meters per second over 10 meters per second. So the inverse sine of 8.85 over 10 is going to be equal to this theta. You plug that in, 8.85 over 10. You get that this angle is equal to 62.25 degrees. And that's the last torture problem that I have for you guys. Oh snap, okay, you didn't hear that. That's the last torture problem I have. I would give you guys another one, but I feel like I covered everything and probably scared y'all for the rest of y'all's life. But trust me, I showed you guys the hard questions of this stuff. I didn't show you any of the easy stuff. This was really advanced things. And if you rewatch this probably once or twice, just the questions part, you can learn the way I think about this stuff, and you can apply it to yourself, which in the end is what we're trying to do, me and Tony, is we're just trying to help you guys. So if you rewatch it again, and maybe again if you need to, so you can understand what we're doing, why we're doing it, and if it's like logically, like what conceptually it means, and you can completely understand that, then I can 95% guarantee you that you have officially mastered projectile motion, and you will thank the Lord himself for being able to master projectile motion. But I want to rewrite for you guys these two equations. Over G is equal to T. Delta X is equal to V initial squared sine 2 theta over G. These two equations can be dangerous, like I said before. If you can tell yourself that you mastered projectile motion, if you go onto Google and search up projectile motion questions, or even hard projectile motion questions, and you completely solve them, like off the top of your head, you know what to do, you know the process you're going to do it in, and all that stuff, then I tell you to memorize these, because they would save you time. And if you write these on the AP exam, they are correct. They won't take a point off for you, or you won't lose a chance at any point, because these are correct equations. People use these, not in everyday lives, but whenever they need to answer projectile motion questions. These questions are dangerous though. If you feel like you haven't mastered them, don't try to memorize these. Don't memorize these just for the shortcut way, because it won't help you in the end. Trust me on that. I want to say again that this delta x is where this is the angle. This delta x is right here. This is the delta x that you're looking for. And the time it takes is the time whenever the ball, or whatever it is that's floating is on this. It hits the ground again. Alright, that's it for projectile motion with me. I really hope I scared you guys. And yeah.